Let's look at example 4 from section 3.5. So we want to find the maximum profit and the number of units that must be produced and sold in order to yield the maximum profit for a company with a revenue equation of R of x equaling 100x minus x squared and a cost function C of x equaling 1/3 x cubed minus 6x squared plus 89x plus 100. Assume that the revenue and cost are given in thousands of dollars and x is in thousands of units produced. So for this problem, since we're looking for maximum profit, we want to use the equation that profit is equal to revenue minus cost. So the first thing to figure out is what we know. So let's start on step 3. We don't need to draw a picture in this case. And so we're going to jump to what we know. We know that revenue is 100x minus x squared. We know cost is given also. So then what do we want? So we want to know the maximum profit. So that's going to be essentially P of x evaluated in terms of our value of x that we find is the maximum. And we want to know the number of units. So that's going to be our value of x. So now we need to find our function and its domain. So use the fact that profit is revenue. So the money coming in minus cost, the money going out. So our profit equation here, P of x, is going to equal to that revenue function we're given, 100x minus x squared, minus the entire cost function, so minus 1/3 x cubed minus 6x squared plus 89x plus 100. Now, be careful with this. A common mistake I'll see is students won't subtract the entire function. They'll just change the sign of this very first term and say minus 1/3 x cubed and leave the rest of it as it is. But remember that subtraction is actually going through to the entire function, so it's going to change the sign of everything. So it ends up being 100x minus x squared minus 1/3 x cubed plus 6x squared minus 89x minus 100. And then we can simplify this by combining our like terms. So we end up with a profit equation, P of x, equal to negative 1/3 x cubed plus 5x squared plus 11x minus 100 whenever we combine those terms. So our next piece we need to think about once we have your function is always what is your domain of that function. And for the word problems, remember that's going to be what is the domain in terms of the problem. So even though we know this equation is a polynomial, our domain's not going to be all real numbers because we're talking about a number of units of something, and you can't make a negative number of units. So our minimum that you can make is 0 units. And then there's not a maximum in this case. You can theoretically make as many units as you want to make. So our domain for this problem is going to be the open interval from 0 to infinity. So the next step is we need to find our critical numbers and then test those critical numbers to make sure that they give us the type of extrema that we're searching for. So remember, to find critical numbers, you start out by taking the derivative of that function. So P prime of x in this case is equal to negative x squared plus 10x plus 11. And so to find critical numbers, remember you're always asking yourself, where is the derivative equal to 0 and where is the derivative undefined? Now we know this derivative is a polynomial, so it's never undefined. So we don't have to worry about that leg, but we do have to find where it's equal to 0. So we're setting the equation negative x squared plus 10x plus 11 equal to 0. Now, usually if you see a quadratic, you think factoring if you can. So to factor this, it's going to be a little bit easier if we get rid of that negative leading coefficient. Now, since this equation is equal to 0, we can just divide both sides by a -1, and we're not going to change the equation any. So x squared minus 10x minus 11 equals 0. And now that's a little easier to factor. So this is going to factor as x minus 11 times x plus 1 equals 0. So now that means x minus 11 equals 0, which gives us the number x, critical value x equals 11, and x plus 1 equals 0, which gives us a critical number x equals -1. So go back, check to see if you have to test both of these critical numbers. So look back at your domain. In this case, our domain was 0 to infinity. So because of that, we know we can throw out x equaling -1. It's not in our domain, so we don't have to test it. So the only one we have to test as a critical number is x equaling 11. To test that critical number, do the second derivative test when you can, right? And then if it fails, go to the first derivative test. But second derivative test is always easiest for the most part. So our second derivative of this profit function is going to be -2x plus 10. So now plugging our critical number of 11 into that second derivative, you get -22 plus 10, which we only care about the sign. That's going to be less than 0 since 22 is larger than 10. So we take the negative sign there. And so since that second derivative evaluated at our critical number is less than 0, then we know by the second derivative test for relative extrema that x equaling 11 is a relative max. And so we go back and check. We wanted max profit. We have max, so we're good. So now we just answer the question that we were asked. So we were asked to find the maximum profit and the number of units. So our number of units is going to be our value of x, so 11. But x is in thousands of units, so we actually want to make 11,000 units, not just 11 units. And then to get the max profit, you want to plug in 11 into your profit function, so P of 11. And so if you plug in to find P of 11, you're going to get out 182.333. And that 3 is really repeating on and on and on. So that means, again, since revenue and cost are in thousands of dollars, our profit's going to be in thousands of dollars. So we need to move that decimal place to the right 3. So our maximum profit's actually going to be $182,333 for this problem.